is the universe? Hi, everyone. I'm Mr. Pinola, and I want you to start off today by thinking about that question. What is the universe? A lot of people hear that and they can't give a great answer to it. But what you often hear people say is that the universe kind of contains everything around us. All the planets, moons, stars, everything is contained inside the universe. Today, we're going to talk about universal forces. Let me put that up here on our board. And universal forces are forces that exist everywhere in the universe. These are kind of like the main categories of forces that you're going to find no matter which planet or star you're on in the entire universe. They always exist, and they always exist in the same way. There are 4 types of universal forces, and we'll learn about all 4 different types and some of the specific properties of each in our lesson today. The first category within universal forces are electromagnetic forces. Now, maybe you notice 2 different parts to this word, electromagnetic. Now, we learned about electromagnetic waves before, but notice electro implies electricity, and magnetic obviously implies magnetism. So our first category of universal forces, named electromagnetic forces, contain any forces that tell us how electricity or magnetism work. And as we learned from electromagnetic waves, electric and magnetic fields constantly interact with each other. So let's take a look first at the electricity part of electromagnetic forces. Well, electricity is governed by the presence of 3 different subatomic particles. What do I mean by subatomic? Sub means kind of inside or below. So subatomic means inside the atom. Do you know what types of particles make up all atoms? You might have learned about this last year or in a previous class, but there are protons, neutrons, and electrons. Notice the word electricity sounds a bit like electrons. That's where the name electricity comes from. Now, what do we know about protons, neutrons, and electrons? Well, they all have a charge. What charge do protons have? If you said positive, you'd be right. Neutrons have no charge. And electrons have negative charge. Now, maybe you've heard the old-time phrase, opposites attract. And it's true when dealing with electric forces. If you were to have a proton and an electron, and you were to bring those 2 together, they would attract each other. But if you were to bring a proton near another proton, they would repel or push away from each other. Notice that 2 protons would push away from each other. That's because they both would have the same charge. They'd both be positive. But electrons, if you had a proton and an electron, they would move towards each other. They would be attracted because they are opposite charge. One is positive, one is negative. What do you think would happen if you had 2 electrons? If you said they would repel, you're right. That's because 2 electrons would have the same charge, and so they would push away from each other. Opposite charges attract. Like or the same charges repel or push away. That's how electricity and electric forces work. But what about the magnetism part of electromagnetic forces? Well, there are two different types of magnetic poles that we can have. Maybe you've heard of the magnetic pole. There are north poles and there are south poles. Now, we're not talking about North Pole, like where Santa Claus lives. We're not talking about the South Pole, like at the bottom of a globe where you might find a bunch of penguins. No, we're talking about two ends of a magnet. So if you were to have a bar magnet, let's say, one end of the magnet would be the North Pole end, and the other would be the South Pole end. And every magnet has a North Pole and a South Pole. But how do these poles interact with each other? Well, we can take a look at that by looking at magnets that are aligned in a certain way. So, for example, here is a refrigerator magnet. This clip can go on the refrigerator. I use it to hold up a calendar. And notice my board is magnetic, and so I can put the clip right on my whiteboard. Now, this magnet is a north pole facing outwards. The south pole is facing inwards. Remember, all magnets have both a north and a south. It just depends which way they're facing. So the north pole is facing out. I'm going to bring the magnet that's on the back of this red clip near the silver one and watch what happens. They're clearly attracted to each other. Now, I told you that this was a north pole facing outwards. So what kind of pole do you think this is on the red clip? If you said south, you'd be right. That's because opposites attract. North and south attract each other. But what about north and north? Here on this orange clip is another north pole. This is a north pole as well. I'm going to bring them near each other. Let's watch what happens. Even if I bring them real close, they won't actually touch. They're kind of pushing away from each other a little bit. And if I bring this real close to the screen, you can see that. Let me show you what the red one looked like up close. I couldn't even keep them apart. That force was so strong. But the north and north, they repel each other. So magnets operate much the same way that electricity does, except instead of positive and negative charges, we have north and south poles. Still though, the same rules. Opposites attract, like charges or the same charges or poles will repel or push away. So we learned a little bit about our first type of universal force, the electromagnetic force. And that tells us, for both electricity and magnetism, that opposites attract. So opposite charges, positive and negative, will be drawn towards each other. And likes repel. So the same charges, like two positives or two negatives, will repel each other. And specifically that works with electricity and with magnetism. So my example was with charges, but that could also work with north and south poles that would attract each other. But north and north would repel, and south would repel. But now let's learn about the second and third type of universal force. And these are closely related to each other. One is called the strong nuclear force. And the other is called the weak nuclear force. Let's take a look specifically at what the strong and weak nuclear force do. Here's an atom. And so to demonstrate the strong and weak nuclear force, we first need to think about this word, nuclear. What does nuclear mean? Well, nuclear means that it deals with the nucleus of an atom. Do you know where the nucleus of an atom is? If you said right in the middle, you'd be correct. So the nucleus of an atom would be in the middle. I am not drawing it to scale right now usually the nucleus would be much smaller compared to the size of the atom. But inside the nucleus, we have a bunch of different subatomic or small particles. Do you know what kinds? Well, remember from what we did before, we talked about that there were three types of subatomic particles: protons, neutrons, and electrons. Now, the electrons hang out outside the nucleus. They're all in this big circle, but they're not in the nucleus itself. Within the nucleus are the other two types, protons and neutrons. Let me draw a couple of them in. Here's 6 protons, and now let me draw 6 neutrons. For you people who like chemistry, this would be an atom of carbon because it has 6 protons. But anyway, 6 protons and 6 neutrons inside the nucleus. Now, the neutrons have no charge, and that means that they have no effect on attraction, drawing together, or repulsion, pushing apart. So when we look at the nucleus, when we look at it electrically, we have to focus on the positive charges only. So let me take the neutrons out of here. We know they're there, but they're not actually affecting anything. Now, 6 positive charges, they're all the same. What do like charges do? If you said repel, you'd be right. They're all going to push away from each other in every direction. So they repel each other, and the nucleus would split apart. But wait, the nucleus of an atom doesn't just split apart on its own. I wouldn't exist if that were the case. Instead, the nucleus is held together by these little bonds. So we have a mystery force that keeps the nucleus together. What kind of force is that? Well, it's actually 2 different forces. It's the strong and the weak nuclear force working together to keep the nucleus of an atom from splitting apart. So the strong and the weak nuclear force work together. We as scientists are still discovering more about the difference between these 2 forces, but what you need to know is this: these nuclear forces keep the nucleus from splitting apart. The nucleus of an atom is stable. It doesn't split apart on its own, and that's thanks to the strong and weak nuclear forces. So both of these forces are very powerful, but they're very powerful only at short distances. The nucleus is very tiny. We can't even see it with our eyes. And so even though the strong and the weak nuclear force are great at keeping the nucleus of an atom together, they only work at very short distances, like the size of a nucleus, a distance that we can barely see with our eyes. And that is very different from the last universal force that we'll learn about in a second. The last type of universal force is the one you're probably most familiar with, and that is gravitational force, or the force of gravity. It's the force that's bringing me towards the center of the Earth. Now, I don't actually move there because the ground is keeping me up, but gravitational forces will always draw 2 objects together. A gravitational force never pushes. Gravity is never going to send you flying up into the air. It's always going to pull you towards the center of the Earth. Now, did you know that the gravitational force can also act between different planets? It's true. For example, if we were to have the Earth here's our Earth, we'll draw a couple continents in there, and the Moon, which is much smaller than the Earth. there would be a gravitational force bringing these two together. So the Earth would pull on the moon, and the moon would pull on Earth. Just like if you were standing on the surface of Earth. Obviously, I'm not drawing my picture to scale. You would be pulled towards Earth. But did you know that you pull back up on the Earth? It's true. Any two objects that have mass, you and the Earth, the moon and Earth, or really any two objects you can think of, are going to put gravitational forces on each other, bringing them towards each other. Action 1. So then how come the Earth pulls you towards it and you pull on the Earth? But you move a whole lot when that happens, but the Earth doesn't move. Well, according to Newton's third law, the force that you put on the Earth is equal to the force that the Earth puts on you. Remember, for every action, there is an equal and opposite reaction. It's the same with the moon. The moon pulls on Earth with a certain amount of force, and the Earth pulls on the moon with the exact same amount of force. But then, how come the moon will revolve around the Earth, but the Earth doesn't seem all that affected by the moon? The answer is it's because they have different masses. So even though the forces are the same, the objects respond differently because they have different masses. Let me show you what I mean by that. Here are two objects. I have a large bouncy ball that's yellow with black spots, and I have a small red bouncy ball. Right now, these both have mass. So they are going to put gravitational forces on each other. They're going to move towards each other. Now, that won't actually happen in real life because the force is so weak that they won't actually move because of that force, because we have things like friction and air resistance. But they are going to pull each other. Did you know that the big ball pulls on the small one with the exact same amount of force that the small one pulls on the big one? It's true. If the large ball pulls on the small one with a force of 5 newtons, let's say, then the small one will pull on the larger one with the exact same amount of force, 5 newtons. And that is called universal gravitation, that two objects can pull on each other with the exact same amount of force. So the last type of universal force is gravitational force. Gravitational force works well at long distances. But it's not quite as strong as the nuclear forces or electromagnetic forces. So if you want a force that's going to act really far away, use a gravitational force. It is very effective over long distances, but the strength of that force isn't quite as strong as some of the other ones on this list. I hope you learned something today about universal forces. These forces exist everywhere in our universe. Electromagnetic forces, which deal with the interactions between electric particles and each other, and magnetic poles and each other. The strong and the weak nuclear force, which help to keep the nucleus of an atom from splitting apart. And lastly, gravitational force, the force that obviously keeps us on Earth, but will also draw two objects, like the two bouncy balls we saw before, towards each other. These 4 different forces are the basic forces that make up life. And next time, we're going to dive a little bit deeper into one of the more familiar forces to us, gravitational force. But for now, you just need to know that these 4 types of forces make up the group we call universal forces. And I'm glad that now we know a little bit about how how each of these work. Thanks for watching.